On February the 20th, 2026, workers lifted the final arm of a 17-meter cross into the Barcelona sky. The Sagrada Familia became the world's tallest church, 144 years after construction began.
A crane hoisted a star above Barcelona in 2026, and a 144-year building finally became the tallest church on Earth. How did a project that began in 1882 survive a civil war that destroyed original drawings?
Workers laid the foundation stone in 1882. The building has survived 2 world wars, a civil war that destroyed the construction plans, a pandemic that halted work entirely, and technological revolutions that changed how humans build.
Decades of stop-and-start work, and a pandemic to reach the sky. This is Antoni Gaudí's radical experiment. Tree-like stone columns, hyperbolic windows, and a 172.5-meter central tower topped by a 17-meter cross, paired with modern fixes, prefabricated stone panels, hidden steel cores, and millimeter tolerances that finally made the impossible finish possible. Why it took so long? The gap between the first foundation stone and the final pinnacle is startling. Construction began in 1882. Antoni Gaudí died in 1926, with less than 1/4 of the basilica finished, and only in 2026 did the structure finally reach its highest point. That span of 144 years reads like a chronicle of interruptions, political upheaval, economic uncertainty, and shifting technology all left their mark. Some pauses were external and sudden, like wars and a global pandemic that halted work. Others grew out of the project's own ambition and complexity. The result was a stop-and-start building process that stretched across generations and styles. Wars did more than slow work. They sometimes destroyed the very blueprints of progress. The Spanish Civil War inflicted a particularly brutal blow when Gaudí's workshop and most of his models were smashed, erasing the primary tangible record of his methods. Surviving fragments and memories became the only guide for architects who followed, turning reconstruction into an act of interpretation rather than straightforward assembly. That loss converted routine masonry into an exercise in historical forensics, where every decision required careful cross-checking against the few authentic sources that remained. Financing shaped the tempo as much as politics. The Sagrada Familia was conceived as an expiatory church funded by public donations, which meant construction depended on the ebb and flow of charitable giving. Periods of rapid progress alternated with long stretches of slow accumulation because the workforce and material purchases rose and fell with funding. Relying on variable donations turned a once predictable building schedule into a century-scale endurance test. Ambition also created technical bottlenecks. Gaudí transformed a conventional Gothic brief into an experimental architecture that pushed stone, geometry, and craft to new extremes. Curved vaults, twisting columns, and uniquely shaped surfaces did not lend themselves to mass production or the typical mason's toolkit of the late 19th and early 20th centuries. Every novel form demanded bespoke solutions, which slowed work and increased the skill required to continue the project faithfully. The destruction of original models magnified the consequences of Gaudí's novelty. With plaster casts and hanging chain models broken or lost, later teams could not simply pick up where he left off. They had to reconstruct intentions from fragments, photographs, and the surviving pieces of his work. That reconstruction required time, debate, and sometimes reinterpretation, because different architects brought varied readings of Gaudí's principles. Each choice affected future construction methods, material selections, and structural logic. To understand how it began, you have to go back to those first meeting rooms and the humble donations that launched an impossible idea. Origins and early design. The Sagrada Familia began in 1882 when a group of Catholics in Barcelona decided to build an expiatory church financed by public donations, an unusual model that tied the project directly to the will and wealth of the city's people. Initially, the plan followed a conventional Gothic approach with a familiar vocabulary of buttresses and vaulted spaces. That early outline set the stage for something recognizable and rooted in ecclesiastical tradition. Funding through donations, however, meant the building's pace would always be tied to the community's priorities and fortunes. A year after construction began, in 1883, the young architect Antoni Gaudí assumed control and rapidly transformed the program. He abandoned strict replication of Gothic tropes in favor of a radical reinterpretation that treated structure, ornament, and theology as a single integrated system. Gaudí's approach re-envisioned the basilica not as a stitched-together program of parts, but as a unified organism informed by natural forms. His design choices shifted the project from a large church to a long-term architectural experiment. Gaudí drew extensive inspiration from nature and geometry, redesigning columns to resemble tree trunks, vaults to follow natural curves, and towers to rise like rocky peaks. He believed structural form should emerge from function and natural principles, rather than purely historical precedent. This philosophy produced spaces where load paths flowed organically, columns branched near the ceiling, and light became an active element of the architecture. The result was a building that looked both ancient and utterly new. Gaudí preferred to use physical models and hanging chain models to calculate structural forces instead of two-dimensional drawings because these tactile models showed him three-dimensional paths of compression and thrust. The models enabled the conversion of advanced geometrical shapes into practical manufacturing methods, while serving as a foundation for masons to create stones that matched their specific design requirements. The technique allowed Gaudí to create new designs which he could not test through conventional drawing techniques of his era. The physical models developed by him became the main resources for future researchers. From the start, Gaudí planned a symbolic cluster of towers, 18 in total, each carrying explicit religious meaning embedded in their hierarchy and placement. The design included 12 lower towers for the apostles and 4 taller towers for the evangelists, and 1 tower dedicated to the Virgin Mary, and the tallest central tower which would honor Jesus Christ. The program transformed the entire composition into a vertical catechism, which taught through its architectural design and visual elements. The project became more difficult to complete because the towers increased in size and their symbolic functions raised the stakes for public involvement. Yet Gaudí's ideas were not merely eccentric ornament, they were a complete rethinking of form and structure that would test every builder who followed. Gaudí's radical vision. Walking into a Gaudí space feels less like entering a building and more like stepping into a living forest carved from stone. His columns rise and branch in ways that mimic tree trunks dividing into limbs. That botanical metaphor was both aesthetic and structural. Columns were designed to transfer load internally, so the vaults could be supported without massive external buttresses. This internalization of forces allowed Gaudí to create wide, luminous interiors where light and space felt continuous rather than compartmentalized. The effect was an immersive architecture that blurred the boundary between nature and structure. Those columns do not maintain a single section as they rise. They twist, change, cross-section, and split as they approach the vaults, producing complex, three-dimensional geometry that few stonemasons of the 19th century had encountered. A column might begin hexagonal at the base, become octagonal midway, and then branch into multiple members near the ceiling. Crafting stone to that evolving geometry required careful modeling and, ultimately, new fabrication techniques to match Gaudí's precision. The result is a support system that reads as sculptural and functional at once. Gaudí also rethought openings and light. Instead of rectangular windows, he used hyperbolic and parabolic geometries that not only softened and diffused sunlight, but also reduced load on the walls. Stained glass was not an afterthought, but an intrinsic part of the spatial strategy. Blue and green tones on the east create gentle morning light, while reds and oranges on the west ignite the interior at sunset. The glass panels were calibrated to turn sunlight into a moving, colored atmosphere that changes with time, shaping the emotional experience of the nave. Light, for Gaudí, was structure in a temporal sense, as much as it was ornament. The combination of form and light resulted in technical effects, which affected the whole system. The construction required special methods to cut and join and support stone blocks, because the building design used curved surfaces which did not follow standard angles and created custom window designs. The continuous flowing forms which Gaudi preferred made standard block shapes and repetitive courses unsuitable for his architectural needs. The design required all elements to be created as components of a unified geometric system which mandated all workers to maintain high standards of precise work. Gaudi preferred tactile methods, which allowed him to study physical models through three-dimensional plaster models and hanging chain models, which he used to study thrusts and compression. The physical models provided both structural and proportional information, which remained inaccessible through the plans because they contained free-form surfaces. He used the models to study how shape and force interacted until he achieved his desired results. The remaining examples of those models which had originally existed were viewed as sacred keys, which revealed the existence of sacred keys to achieving building completion. His artistic vision required him to select specific materials for his work. Gaudi specified Montjuic stone as his building material because he wanted to use local materials which possessed functional characteristics. Teams needed to search for replacement stones from different quarries because the original sources became depleted, and they tested each block for its strength and structural properties and its visual attributes to achieve visual and structural uniformity. The construction team needed to achieve two objectives because they had to use original materials while constructing taller structures, which required them to establish an internal balance between historical accuracy and operational efficiency. The construction process for multiple decades stayed affected by the conflict between using original materials and the need for materials which were more accessible. To finish the basilica faithfully required both respect for Gaudi's methods and the invention of new techniques to realize forms that his own era could not complete. War, loss, and reconstruction. The Spanish Civil War damage was decisive. Gaudi's workshop was burned, and most of his plaster models and notes were smashed, removing the physical record of how he translated geometry into stone.
Gaudi knew he wouldn't be able to complete such a monumental project in his lifetime. So he had to make sure future architects would be able to understand his designs once he was gone. And for that, he relied on the principles of geometry.
Without those models, the people who followed him faced a fragmented archive. Photographs, a few surviving models, and memory became the only reliable clues. That loss turned continuation into interpretation. Architects and masons could not rely on a complete blueprint, but had to reconstruct intent from remnants. Every gap in the archive forced choices that would affect structure, aesthetics, and the future pace of construction. Survivors and later architects pieced together what they could from the fragments that remained, treating each recovered model as essential evidence of Gaudi's method. They combined the remaining plaster casts, sketches, and Gaudi's built work to extrapolate forms and load paths that were never fully documented on paper. This reconstruction was painstaking because Gaudi's process privileged three-dimensional modeling over exhaustive drawings, so reinterpretation required both technical knowledge and historical sensitivity. The result was a slow, careful effort to remain faithful while filling in blanks with reasoned engineering and design judgment. The destruction shifted the project's character from straightforward construction to an archival and creative endeavor. Teams became custodians and translators of a lost master's techniques. Different architects across decades read Gaudi's remaining cues in different ways, which introduced stylistic and methodological variations into the work. Those variations were not mere cosmetic differences. They influenced structural decisions, stone choices, and how new elements integrated with old. Over time, debates about fidelity versus adaptation became part of the building's social and professional history. External events compounded the difficulty. The basilica survived 2 world wars and later a global pandemic that forced construction to stop, each episode interrupting labor, funding, and supply chains. Interruptions like these meant craftsmen and engineers who understood particular phases would disappear or retire, taking tacit knowledge with them. Restarting work required regaining momentum, retraining teams, and sometimes revisiting earlier decisions that no longer matched available materials or methods. These starts and stops extended the schedule dramatically and increased the cost of continuity. Rebuilding in the aftermath of destruction also meant adapting to changing technologies and standards of safety. As architectural practice modernized, so did the tools available to interpret and manufacture Gaudi's complex geometries. Later generations introduced structural analysis software, digitized models, and mechanized stone cutting, tools Gaudi had not had, but that could help realize his forms more accurately. Incorporating these tools required new skill sets and changed how decisions were tested before being executed on the building. That shift gradually altered the rhythm of construction from artisanal improvisation to a hybrid of craft and engineered precision. The long chain of custodianship created a unique cultural responsibility. Every generation had to balance respect for Gaudi's intentions with practical needs of the present. Where originals were missing, teams looked to Gaudi's built fragments and surviving models as the primary authority, but judgment calls were inevitable. Those calls affected not only aesthetics, but also structural strategy, procurement, and how visible new work would be. The process became as much about stewardship and interpretation as it was about laying stone. Reconstructing a shattered legacy demanded not only archival sleuthing, but also fresh methods of making, ways to turn modern precision into a language that could speak Gaudi's forms. Modern fabrication breakthroughs. Achieving Gaudi's towering ambitions required rethinking how stone was produced and assembled. Building a stone tower above 170 meters cannot rely on traditional layer-by-layer masonry alone. Engineers and builders moved toward prefabrication, dividing the tower into large structural modules manufactured off-site and assembled on location. That shift reduced risky work at height and concentrated the most critical precision tasks in a controlled environment. Prefabrication also made quality checks repeatable and measurable before any element left the workshop. Each panel used for the upper towers is essentially a complex assembly made from 16 stone blocks, each cut with computer numerical control machines to match three-dimensional design data. CNC machining allows the curved and twisted surfaces required by Gaudi's geometry to be reproduced with millimeter accuracy, something hand carving alone could not deliver at scale. After the machined blocks are fitted together, technicians assemble the panel to verify geometries and connections before transport. This modular logic translates an unrepeatable bespoke form into discrete, testable units. Once the stone blocks are assembled into their panel geometry, hidden steel components are integrated to increase stability and continuity across the tower. Steel bars and embedded connectors run within the panel to provide tensile capacity and to join adjacent modules securely. That hybrid approach preserves the visual and tactile qualities of stone while compensating for stone's weakness under lateral and tensile forces. The concealed metalwork allows panels to act together as a unified structural system rather than as individual stacked units. Each completed panel is designed to function as an independent structural unit capable of bearing loads and transferring forces to the levels below. So the tower is put together from self-contained pieces rather than many loose stones. 8 such panels are assembled to form a complete level of the tower, creating a repeatable rhythm for vertical construction. Because panels are engineered as units, their interaction is analyzed before installation, which reduces surprises when elements rise into position. This approach also makes it possible to test load paths in the factory before the panel ever leaves the workshop. Prefabrication vastly improved quality control. Panels are inspected for dimensions, tightness of fit, and load-bearing capacity in the workshop, which lets engineers detect and adjust deviations under ideal conditions. That inspection regimen is critical because once a piece is lifted into place dozens of meters above ground, on-site corrections become far more difficult. Working in a workshop also speeds production and reduces risk for workers compared with stone-by-stone carving at height. The net effect is both faster assembly and a safer process overall. Speed is a measurable advantage. The modular method enabled erection rates that engineers estimate to be roughly 16 times faster than traditional stone-by-stone techniques. That factor is not just convenience. It changes project timelines from decades-long drifts to predictable phases with concentrated bursts of assembly. Faster erection reduces exposure to weather windows and logistical delays, improving coordination for cranes, scaffolding, and specialized crews. In a project stretched across generations, compressing some activities through modularity makes the final stages achievable. In doing so, the project found a practical path to complete Gaudi's most audacious geometries without abandoning the material language he championed. Hidden steel and structural tricks. Stone is magnificent under compression, but poor at resisting continuous horizontal forces like wind and seismic vibration. And that weakness became a critical problem as the towers climbed higher. Engineers responded by turning the panels themselves into composite units. Stone faces remained visible, while internal steel elements carried tensile and shear demands that stone could not. High-strength steel bars, embedded connectors, and steel cables run through each module to tie elements together vertically and to provide continuity across joints. When those cables are tensioned, individual stone blocks stop behaving as discrete pieces and begin to act as a single, locked mass. The effect is similar to a monolithic stone structure in load path, but with far greater control over how forces move through the tower. Steel provides ductility and redistribution where stone would crack. Designers used the steel not as a visual element, but as a hidden skeleton, placing tensile members where lateral loads might otherwise cause separation or excessive deflection. This allows the exterior to preserve Gaudi's stone aesthetic while meeting modern safety expectations for tall masonry. Because steel components are internal, inspection and quality control focus on connection points and the behavior of the composite assembly rather than on exposed metalwork. Integrating steel also changed how panels were designed in terms of assembly and tolerances. Panels are prefabricated with cavities and ducting to accept bars and cables, so that connections align precisely during workshop assembly and on-site joining. Vertical continuity is achieved by running reinforcement through successive levels and then tensioning or locking them, creating a continuous structural spine embedded within the stone. That continuity is essential for controlling vibrations and for ensuring that dynamic loads are shared rather than concentrated. The technique transforms a stack of heavy panels into a coordinated, resilient tower. Vibration control was a driving design requirement as much as strength. At heights above 170 meters, wind-induced oscillations and gust load variability can produce damaging cyclic stresses, if not mitigated. The steel framework and tensioned cables increase stiffness and provide energy dissipation paths that reduce amplitude of motion under wind or seismic events. Designers used analyses and testing to tune the stiffness and damping properties of the composite system, balancing rigidity with the capacity to absorb transient loads. This tuning made it possible to preserve stone as the visible material without exposing it to repetitive stresses it cannot tolerate. The hybrid system also simplified some repair and adaptation strategies. If a connection or cable needs inspection or replacement, engineers can access specific conduits or anchor points in a controlled manner, addressing wear without dismantling entire stone assemblies. That serviceability extends the structure's lifespan and gives conservators predictable maintenance pathways. It is a pragmatic solution for a building meant to last centuries, but assembled across generations with evolving technologies. The result is both a conservation strategy and a modern structural logic. Embedding steel required careful detailing to avoid creating stress concentrations within the stone blocks themselves. Anchor plates, transition pieces, and bearing interfaces are all designed to spread loads and to avoid point stresses that could fracture natural stone. Bolts and dowels are recessed or fitted into cavities that distribute pressure across larger surfaces, and engineers model contact stresses to ensure long-term performance. Those details are invisible to visitors, but vital to the health of the structure. They reconcile the brittle nature of stone with the ductile behavior of steel. Good detailing turned an aesthetic ambition into a durable engineering system. The hidden framework solved a core engineering dilemma, but it also set the stage for another set of challenges centered on the stones themselves. Materials and precision craftsmanship. Natural stone remained the primary material because it is central to Gaudi's aesthetic, but sourcing and testing that stone became an industrial-scale operation over decades. Gaudi originally used Montjuic stone, prized for local character and workable properties, but quarries depleted, and later teams had to locate substitutes with matching color and durability.
The Montjuic stone quarry is now closed, so they must find a way to replicate the look of Montjuic stone.
Each candidate block underwent strict testing for compressive strength, internal structure, and visual consistency before being approved for use on the basilica. Those tests were essential to ensure new material behaved compatibly with existing masonry and preserved the intended appearance. Quarrying today involves extracting very large blocks with modern cutting systems and transporting them to fabrication workshops as massive raw pieces that may weigh tens of tons. Once in the workshop, three-dimensional design data govern the entire fabrication process so that each curved and twisting surface is matched precisely to digital models. Computer numerical control machining cuts complex geometries with high repeatability, producing surfaces that would have been prohibitively time-consuming by hand. After machining, technicians refine and finish the pieces by hand to eliminate the smallest deviations and to preserve the carved quality expected in Gaudi's work. Different parts of the basilica call for different stones depending on load and expected wear, so the program uses a variety of materials chosen for mechanical properties as well as color. Lighter stones appear in columns and elements carrying smaller loads, while the heaviest, most durable materials are reserved for the central columns and primary load-bearing members. For the most demanding central columns, builders used red porphyry quarried in Iran, a stone known for exceptional hardness and durability. Selecting materials by roll lets the complex support system perform efficiently while maintaining a coherent visual language. Craftsmanship remained crucial, even with machine precision. After CNC roughing, skilled masons and stone technicians hand-finish joints, textures, and sculptural details to ensure each block sits perfectly with its neighbors. That handwork resolves the last fractions of deviation and guards against cold, machine-made surfaces that would break the tactile quality of the interiors. Combining mechanized cutting with artisan finishing preserves both speed and tradition. It is this hybrid that lets the basilica read as both ancient craft and contemporary engineering. One practical advantage of modern fabrication is speed. Tasks that might have taken weeks of hand carving can be reduced to hours with CNC roughing plus finishing, which became essential as the project entered its final, time-sensitive phases. Faster component production shortens the workshop-to-site pipeline and supports just-in-time assembly of panels, aiding coordination with crane lifts and structural tie-ins. But speed was never allowed to replace quality control. Each finished block must pass dimensional checks and visual approval before being released. That insistence on inspection safeguards both structural performance and the building's aesthetic integrity. Tolerances are astonishingly tight. Panels and blocks are produced and inspected so that bolt holes and mating surfaces align with tolerances on the order of 1 millimeter, and on-site correction is sometimes required when small deviations occur. Because each panel weighs several tons, correcting misalignment demands careful jacking, grinding, or controlled re-drilling rather than brute force. These tight fits ensure continuous load paths and prevent local stress concentrations, which is critical when stone and steel must act together seamlessly. The precision is what lets large stone assemblies perform like a single, coherent structure. The stones speak with a handcrafted voice, but behind that voice lies an industrial precision that made the final ascent of the towers possible. Completion moment and timeline. On February 20th, 2026, crews installed the final section of the 17-meter cross atop the central Christ Tower, a decisive moment that pushed the completed pinnacle to 172.5 meters and formally made the Sagrada Familia the tallest church in the world.
The last part of the 55-foot cross was installed on the central tower of the Basilica of the Sagrada Familia in Barcelona, which was designed by Antoni Gaudí more than 140 years ago.
That final piece was both structural and symbolic, a glass and ceramic cross intended to catch and reflect light as a visible capstone to Gaudí's composition. The lift and fixation required precise alignment and exhaustive inspection before the element could be declared permanent. For a project that began in 1882, the day read like a ceremonial closing of a long technical chapter. The central tower's height carries layered meaning. Gaudi originally set relationships between building and landscape. His designs sought to keep human creation subordinate to nature, famously aiming to remain 1 meter lower than Montjuic Hill. Yet the modern realized height of 172.5 meters reflects both historic intent and present engineering choices. The cross itself is a visual beacon intended to complete the basilica's iconographic program, tying the vertical axis to the theological program of the 18 towers. The symbolism and the engineering were inseparable in that final act. Installing the summit element required choreography learned over decades of practice. Prefabrication, millimeter-level tolerances, wind-window planning, and synchronized crane work that minimized oscillation during lifts. Teams had rehearsed the sequence in workshops where panels and connections were fully tested, reducing surprises when the element rose into position. Once in place, every connection point was tightened, sealed, and inspected to verify the composite behavior of stone and hidden steel. The culmination was technical as much as ceremonial, an engineered certainty that allowed a centuries-long promise to take physical form. February 2026 did not mark the end of construction across the whole complex. It marked the completion of the central summit while broader structural work continues. Current plans foresee the main structural system, vaults, and all 18 towers, reaching completion around 2033, followed by final decorative and sculptural finishes targeted for around 2035. Those dates compress decades of intermittent activity into a defined closing phase, acknowledging both the pace of modern fabrication and the remaining artisanal work. Even after the central tower's capstone, much of the basilica's visual and theological program still requires careful craft. When the last major elements are finished, scaffolding and cranes will be removed, and the building will finally be read as a whole, rather than as an assembly in progress. That unveiling is more than cosmetic. Without the equipment and hoists, the urban silhouette will settle, and the interplay of light, texture, and skyline will be visible exactly as the project intends. The experience will allow the public to see how Gaudi's structural forest, stained glass choreography, and tower program work together at city scale. For residents and visitors alike, the removal of construction infrastructure will be the clearest signal that a long era of building has closed. Completion is also a generational achievement in technique. The Sagrada Familia's journey moved from hand carving and plaster models into digital three-dimensional design, structural analysis software, and computer numerical control machining, with each stage contributing solutions that were unavailable to Gaudi. That technical layering means the finished work will embody both the original creative intent and the inventions of successive eras. The building therefore functions as a living record of architectural problem-solving across 150 years, not merely as a static final product. The 2026 Summit installation made the Sagrada Familia's central tower reach 172.5 meters and set a clear path toward full structural completion by around 2033 and final finishes by about 2035. If you enjoyed this deep dive, like the video and subscribe for more engineering stories and megastructure breakdowns.